let's take a solution to this A to D problem that we were just working on before. We have a input voltage here, and we'll go to a 1 kilo ohm resistor. By the way, these values are completely real world. I know a lot of textbooks often give you crazy values, but this will work. So here's a solution to the A to D problem. And if you were to plug this in right here in our original problem, you would solve the aliasing problem. And my question is, what does this do to a 1 radian per second input? And what does it do to a 10 kilo radian per second input? And the point is that we would like it to pass the low frequency, and we'd like it to stop the high frequency. So this whole section is just sinusoidal steady state in, gives you sinusoidal steady state out, but that's not true in general for other non-sinusoidal steady state inputs. And now down here, we're going to solve this problem. So the steps to solving this problem is, firstly, find our H of S. As I write on this board, can everybody see the details? I'm writing kind of small. Can I get thumbs up or thumbs down? Okay, great. So we're going to firstly find the H of S. And then we're going to find our H of S equals J omega equals J, let's see, J1 for 1 hertz. For the first question, for 1 radian per second, for that low frequency. And then we're going to do the exact same thing, but for J 10,000 for a 10 kilohertz, or 10 kilo radian per second, or high frequency. And then once we do that, we're going to find our V out of T for each of those 2 frequencies. Now look, this is important. We are not using Laplace transforms. Some of you are going to get this confused on your homeworks and possibly in your tests, and that would be awful. If you were to try to solve this using Laplace transforms, firstly, you're not solving it for a cosine of 3t input. You'd be taking the Laplace transform of a cosine 3t times u of t. And then you'd end up with something really nasty, with something over with a denominator of s squared plus 9. And then you'd be multiplying it by this h of s, and you'd come up with a very complicated thing with imaginary roots and with real roots, and you'd have to take the inverse transform of that, and that would take you a long time. This is not using Laplace transforms to solve this problem. This is using something else. The only time we're going to use anything that looks like Laplace transforms is to find h of s, not to find v out. Let's do this. We'll rewrite it in the frequency domain. So this is still our R. This is still our 1 over SC. And here's our V out. So Dom, can you tell me what V out is just by inspection? It's a function of Vn.
It's going to be Vn times, V out equals Vn times 1 over Sc.
That's it.
Divided by 1 over Sc plus R.
That's it. So it's just a voltage divider. And we know we do not like this complex fraction, so we're going to multiply top and bottom by Sc. And that gives us 1 over 1 plus SRC. And this tells us what our H of S is. So our H of S, which is our V out over our V in, is going to be what? Let's see, Charles. Given this, what's our transfer function?
I'm sorry, sir. I've completely forgotten.
Well, we want to find our transfer function is V out over V in. Here's our V out, and here's our V in. So what can we do to solve for V out over V in? You've got a V in on this side times something, and you've got a V out all alone. You want to solve for V out over V in. So what will you divide both sides of this by to isolate V out over V in?
You want to multiply both sides by v in?
We don't want to multiply both sides of this by V in because otherwise you'll have V in squared here, and you'll have a V in times V out over here. And what you want to get is V out over V in. So we've got our...
Divide by v out?
That's what we want to do. Divide not by V out, but by divide by... We want to find V out over V in, so what do we want to divide by?
V in.
V in. So when we divide by V in, this goes away. This becomes V out over V in, which is what we want to find. And so now our whole transfer function is just that. And that's not in standard form. Our standard form is to have S alone. So we divide everything by RC. And we'd get that. And when we plug in our numbers for R and C, we get 1,000 over S plus 1,000. So that's our first step. And I'm going to suggest that you try to keep your variables as R's and C's rather than plugging in numbers, because you can see that you know that RC has what kind of units, Connor?
That's tau, right? R times C.
That's tau. And what are the units of tau?
Is that seconds?
Seconds, yep. So RC is in seconds, and that's a great way to quickly check your works. We've got something that's in 1 over seconds in the top. We've got 1 over seconds in the bottom, and S is like a derivative, and the units on a derivative is also 1 over seconds. It's D over dt, which is 1 over seconds. So this is 1 over seconds on the top, 1 over seconds in the bottom. It all cancels, and that's what you want.
Hey, sir,
Okay.
question.
Shoot.
How'd you go from the 1 over 1 plus SRC to the 1 over RC? How'd you get that right there before you got the equals? How'd you get the RCs in there? Where'd that come from?
I just divided through by RC.
Oh, okay.
Yeah.
I thought that was something else. My bad.
I know. Just as easy. Isn't it nice when it's just as easy as it looks?
Yep,
All right.
overthought it.
So we've got our number 1. Let's do our number 2. We're going to find H of J1. So we're going to plug in J1 in for S, and we get 1,000 over J plus 1,000. And we want to find what this is equal to. Here's how not to do it. Do not take out your calculator and plug this in. The way to do it is instead to draw this numerator is definitely 1,000. And this looks kind of weird. These magnitudes are so different. This imaginary part is 1, and the real part is 1,000. So this is bad board technique. But I'm going to just graph up here what does J plus 1,000 look like in magnitude angle form. What we really want to do when we're saying what is it doing to these things, what we really want to find is what is its magnitude. We're really very concerned about more magnitude than phase. So let's find out what its magnitude is. And we know that the rules for magnitude is that the magnitude of a fraction is the magnitude of its numerator divided by the magnitude of its denominator. Well, we know what the magnitude of 1,000 is. It's just 1,000. The question is, what's the magnitude of j plus 1,000? So to find that out, we're going to graph this on the complex plane. It's got a real part, and it's got an imaginary part. And if I was to graph it, 1,000 real parts versus 1 imaginary part would be about that. So that's going to have some magnitude and some angle. So, Phil, can you tell me what its magnitude will be? The magnitude is how far this spot on the line. It's 1,000 parts over here, and it's 1 part up here. How long is that line?
So it's going to be the square root of 1,000 squared plus 1.
That's true. It is going to be the square root of 1,000 squared plus 1. But you're just going to look at that, and you're going to tell me what it is. How long is that line?
Is it just 1,000?
It's just 1,000. I mean, if you want to, you can take
the one's not going to be a whole lot.
It's not going to be a whole lot. In fact, if you were to just take a triangle that was 10 parts here and 1 part here, you can see that the hypotenuse is going to be really close to 10. I mean, it's going to be exactly the square root of 101, which is going to be phenomenally close to 10. So in general, if you want to find the magnitude of a complex number where there's a 10 or greater mismatch between the real part and the imaginary part, you only need to worry about the part that's bigger. So what we just determined was that if you were to write j plus 1,000, which is in rectangular form, in polar form, it would be really close to 1,000 at an angle of 0. So this is going to be essentially 1,000 down here, and this will be 1. And if anyone wants to take their calculator, they can figure it out exactly. It's going to be ever so less than 1. It's going to be something like 0.9999.
So I have a question here.
Sure.
The first thing I thought about doing was just putting in the calculator the 1,000 over j plus 1,000.
Yep.
And then putting the output format as polar.
That's right.
And you get 1 at an angle of like negative 0.057. So would the magnitude here just be 1? You know?
So the magnitude is 1. That's what your calculator is saying, right?
Okay.
Yep.
Sure.
What your calculator is reading out to you is that this whole thing is equal to 1 at an angle of 0. I would think that your calculator would actually read it's 0.99999 at an angle of 0.05 something degrees, which is essentially 1 at an angle of 0, which is 1. Okay.
I got it at an angle of negative, like a negative angle. Negative
Oh, yeah, that's right. That's right. It would be. You're right. No, you are wrong. You've plugged it in wrong. Oh. This will have a positive angle, but then the whole thing will have a negative angle. That's right, because it's 1 over. Okay. Let's do the next one. So this is exactly what you want. At this particular, what this means is that it's neither increasing nor decreasing your signal strength for very low frequencies. It just passes it. Let's do another one. What's the magnitude of h of j 10K? Again, without using your calculator. It's 1,000 over 1,000 plus j 10,000. And using what I just told you, can you tell me, let's see who's up next. Sabine, can you tell me what that denominator is going to be? What is this?
Would that just be 10,000?
That's it. The magnitude would be 10,000. That's right. That's exactly right. If you're to draw it here, you'd have 1,000 off to the right, 1,000, and you'd have 10,000 up here. And so it would be exactly here. So it'd be approximately 10,000 at an angle of 90 degrees. And again, if you throw in your calculator, it'll be slightly different, but it's going to be really, really close. All right, so we got 1,000 over 10,000, and that makes the answer 1/10. And so sure enough, for low frequencies, it passes it. And for high frequencies, it cuts it down to only 10% of what it was before. And if we can do that just when we find V out. So V out of T is going to be equal to cosine of 1T or cosine of, or 1/10 cosine of 10,000 T. And this is the low frequency, and this is the high frequency. Passes and stops. Questions about that? That's the first filter that you've analyzed. And of course, you could have analyzed this filter using phasor analysis entirely, which commingles the whole effect of the input and the system. You could have analyzed it using Laplace analysis, right? If you analyzed it using Laplace analysis, you would have found your x of s, which would be something like 1 over s squared plus 1 for your first example. And then your h of s, which would be, you found out it's 1,000 plus s plus 1,000. So therefore your y of s, your output, would be the product of these two things. Would be 1,000 over s plus 1,000 times s squared plus 1, which you'd factor out into s plus 1,000 plus the roots of this, which are going to be negative, so that'd be s plus j plus something over s minus j. You've got your a, your b star. That would take you a long time to do your complete partial fraction analysis. But using this thing, you can solve it without using a calculator. You can solve it in your head, and you can see what the output is.
So we get
How do you calculate omega cutoff from using this?
Haven't told you that yet, but we're coming close to it. You can actually kind of, well, it's such a good question, I can't help but answer it. When we did the simplification for low frequencies, we could ignore the J. When our low frequencies were 10 times more than our J, let me try this again. It all comes down to the denominator. The J part, how much imaginary part, is from our omega, right? And if we were to solve this in general for any omega at all, it would look like 1,000 over j omega plus 1,000. And so the part that changes, depending upon if it's a low pass or a high pass, is this. And when our imaginary part was a lot smaller than our real part, we could ignore the imaginary part and it would just pass. When it was high frequencies, when our imaginary part became 10 times or more higher than our real part, we could ignore our real part and we could see it just cuts it off. So at what point do you think would be the balance between it passing and stopping? When the imaginary part equals the real part. So for this particular thing, the cutoff would equal 1,000.
My only other question is that before we solved that, this was equal to 1 over RC, which would be frequency. So would it be 1,000 times 2 pi, or would it just be 1,000 if it's an omega cutoff?
How do you convert? Is your question, how do we convert the omega cutoff to a frequency cutoff in hertz?
My question is, up above in step 1, we solved that it was 1 over RC, which would be equal to frequency, right?
All this is in the frequency domain, that's right.
So if that's frequency, if you're transferring it to omega, would you multiply by 2 pi? or divide by 2 pi?
No. All you do is you change S to j omega. I'm not sure if that answers your question. There's two ways to measure frequency, either in hertz or in omega. And we're going to work out everything in omega because it makes the math easy. And then the very last step, if you need a frequency, we'll convert it to frequency. So we analyze this in terms of omega. Do you need to find F? I know this wasn't your question exactly, but do you need to find F cutoff in hertz as opposed to in radians per second? That's no problem. It's just I have to think about this now. Do you divide it or do you multiply?
Divide, I believe.
So then we'd have so then we'd switch it into frequency at the very last point, because you're right. Intuition, we think about frequencies in hertz, but we're going to work it all out in omegas. Yeah, sorry, I misunderstood your question in the beginning. Any others?
For this particular problem, is it just a coincidence that it ended up being the same thing as the resistor 1000 for R omega, or is that or does that happen often? It just end up being whatever the resistor value is.
Is your question, is it just by chance that there's a 1 over RC component in the numerator and a 1 over RC component in the denominator?
No, like in your original circuit, the resistor is a 1K ohm resistor, and we ended up with an omega cutoff of 1000. Is that just a coincidence, or does that happen often?
Just a coincidence. So,
okay.
So what we determined from here, how to find omega cutoff, is it's when the real part balances the imaginary part. That means from our H of S, it's when our 1 over RC is 1. So whenever we get our cutoff is equal to, in general, our cutoff is in general equal to 1 over RC. This is getting more advanced than I really wanted to cover, but it's a good question, so I want you to see. And so this is what our cutoff. And it's because our R and our C are related by 1000 that our omega C happens to be 1000. It's because our 1 over RC is equal to 1000. Any others? Yeah, so it's actually has to do with the product of RC is the reciprocal of our cutoff. Okay.
Thank you, sir.
Yeah. And so now we can complete the design that we began at the beginning of class with the microphone that goes to our low-pass filter, and realize how this low-pass filter is just a resistor and a capacitor connected as a voltage divider that then goes to our analog to digital converter and ultimately to our microprocessor. Some of you might be wondering if this is a low-pass filter, if this section right here is a low-pass filter, what might a high-pass filter look like? And if we swap the position of the resistor and capacitor in this voltage divider, then we get the high-pass filter. Let's analyze for a moment why this is a low-pass filter, just intuitively. If we're talking about very high frequencies, then the capacitor looks like a short, and the high-frequency signal gets shorted directly to ground. On the other hand, if we're looking at low frequencies, for low frequencies, that capacitor looks like an open, and our input signal is connected directly to our output. Similarly, for our high-pass filter, if we have high frequencies, that capacitor looks like a short, and the signal goes right through. Whereas for low frequencies, that capacitor looks like an open, and it just gets blocked right at the capacitor.